Okay, so our next speaker is Yan Gao, and he will talk about invariant graphs in Julia sets and decomposition of rational maps. So please.
Okay, thanks very much for the organizer's invitation. In this talk, I will show how to construct an invariant graph in the Julia set of for a post-critically finite rational map. The construction includes the local part and the global part. The local part relies essentially on the dynamics on the boundary of a fixed Fadel domain, and the global part is based on the cluster exact decomposition. The object connecting the local part and the global part is called maximal Fadel chains. I will explain the details in this talk. So let F be a rational map. In complex dynamics, according to the dynamics, the Riemann sphere is divided into the Fadel side and the Julia side. The orbits of the points in the Fadel side are stable under the perturbation, and the dynamics on the Fadel side is basically clear. So, a central problem of complex dynamics is to describe the structure of the Julia side from all aspects. We just concern about the complementary aspect. So we assume that the map has the best analysis condition. This condition is well known called the PCF condition. That means the orbit of the forward orbit of each critical point is finite, and their union is called the post-critical site, and we denote it by PF. A very important property of a PCF map is that there is a metric near the Julia side such that F is uniformly expanding with respect to this metric. An effective way to characterize the combinatorics of the rational dynamics is by means of invariant graphs. Here, a graph means a finite connected topological graph on the sphere. Invariant means the preimage of the graph is also connected and contains the original one. For PCF polynomials, it is well known that there is an invariant tree containing the post-critical sites. This tree is called Haber tree, and we can classify the PCF polynomials by the Haber trees. But the construction of invariant graphs for rational maps is much more difficult. We list some recent progress. There are invariant graphs for some special rational families, such as the critically fixed maps. That is the rational map with all critical points are fixed points, and the Newton maps. For PCF rational maps with empty Fadel sites, there is an Fn invariant Jordan curve containing the post-critical sites for every large n. A similar result holds for PCF rational maps with Sierpinski Julia site. Recently, we proved that for any PCF rational map, there is an Fn invariant graph containing the post-critical points for every large. However, our construction of the invariant graphs does not essentially use the combinatorics of the Julia side. So the obtained graph does not directly reflect the complexity of the Julia side. We hope to find an invariant graph that contains the feature of the Julia side as many as possible. The question is proposed as follows. For PCF rational maps, are there invariant graphs in the Julia side and homotopic to the Julia side relative to PF? Here, homotopic means there is a homotopy on the sphere with each post-critical point fixed, such that the Julia side deforms to this graph and this homotopy. We also have a combinatory description of the homotopic property. That is the intersection of G and the post-critical sites equals to the intersection of Julia site to the post-grid points. And the 2 points of PF are separated by the Julia site if and only if they are separated by the graph. This is the combinatorial description. And since the graph is homotopic to the Julia site, so this graph, such a graph, directly reflects the combinatorial structure of the Julia site. Moreover, we know that each complementary component of G contains at most 1 point of PF. So the preimage of G under Fk is always connected for every K. A motivation to find such a graph is to study the co-entropy of rational maps. The co-entropy of polynomial is defined to be the topological entropy on the Hilbert tree by Thurston, because the Hilbert tree contains all essential information of the Julia set of polynomials. Still, for the polynomials, we also have invariant graphs consisting of internal rays and external rays, but the entropy on such a graph is 0. So to define the co-entropy for rational map, we hope to find the invariant graph in the Julia site. We think a candidate of the co-entropy is the infimum of the entropy on the invariant graph in the Julia site. So this is one of my motivation to find such a graph. The main theorem of my talk is the following. We say Fp is a marked rational map if P is a finite F invariant site containing the post-critical site. We prove that for any marked rational map, there is a graph in the Julia site such that the graph is homotopic to the Julia site where P, and the graph is Fn invariant for every large n. We see an example. If F is a polynomial, the theorem can be proved by slightly revising the Hilbert tree. In this example, there are 4 subarcs in the periodic Fadot domains. We replace these 4 arcs by the boundary of the Fadot domains, and replace the other subarcs of the trees in the Fadot domains by a suitable choice of the half boundary. This is shown in the right picture. This replaced by the boundary, and the other one replaced by half of the boundary. And this is the desired graph in the Julia site. Note that this Julia site is, this invariant graph is on the boundary of the basin of infinity. So it is natural to ask a general question. This is a local question for invariant graphs. Are there invariant graphs in the boundary of a fixed Fadot domain? To solve this problem, we need to study the dynamics on the boundary of a fixed Fadot domain. In the boundary, there is an important kind of objects, namely circles, and that is Jordan curves. We know that every component of the sphere minus the closure of U is a Jordan domain. So its boundary is a curve, is a circle. On the other hand, each circle in the boundary of U is the boundary of such a component. We will see the image of a circle. In the polynomial case, the image of a circle is a zero circle. But in general case, the image of a circle is not necessarily still a circle. We see an example. This is a cubic rational map. The basin of infinity is a fixed Fadot domain of degree 2, and it has another preimage component U prime. We consider the circle, the green circle, this green circle. And there are some internal rays of U and U prime with the same landing point. This is the like the right arc the red arc. These interarrays are mapped to the green lines, like this. They are interarrays in U. So the image of the green circle must contain the common landing point of the green interarrays. So its image is not a circle. The correct object that describes the image of a circle is called the circle tree. This is the definition. A continuum in the boundary of U is called a circle tree if for any circle C, either C entirely contained in T or the intersection of C and T contains at most one point. We prove a key lemma. It says that the image of a circle tree is also a circle tree. So as a corollary, a circle is a special circle tree. So its image is a circle tree. Similar to the construction of the Hilbert tree in the polynomial case, we can construct an invariant circle tree on the boundary of U. There exists a circle tree T in the boundary of U such that T has finitely many terminal points and circles and finitely many branched points or circles. T is homotopy to the boundary of U where P, and T is F invariant. Finally, every locally branched points of the boundary of U and every circle in the boundary of U is eventually iterated to T. But this T is not a graph because he may contain infinitely many circles. By this study, we can find an example that the boundary of U does not admit an invariant graph. This is our previous rational map. For this rational map, we can prove that for any arc gamma in the boundary of U, the iteration of gamma will finally cover the entire boundary of U. Therefore, there's no invariant graph on the boundary. Positively, we can construct an invariant graph homotopic to the boundary of U in a larger set based on the invariant circle tree. We define EK to be the component of the pre-image component of the closure of U and the FK, and that containing U. So EK is an increasing sequence of continuum. The Fadot chain generated by U is defined to be the closure of the union of this EK. We prove that there is a graph G in the intersection of KU and the Julia side such that G is F invariant and G is homotopic to the boundary of U where P. The sketch of the proof is the follows. So first we have an invariant circle tree T. Within this invariant circle tree, we can find a graph G1 such that G1 has a subgroup G2 isotopic to G1 where P. By isotopic lifting, we obtain a sequence of graph Gn such that each Gn is isotopic to G1 where P. Finally, we prove that Gn converges to an invariant graph G. This is the desired graph. Note that each GK belongs to EK. So the final G is contained in the intersection of KU and the Julia side. In the previous example, this is G1, and this G2, and G3, and so on. So the local invariant graph is clear. Motivated by the Fadot chain generated by U, we can define the general Fadot chains. Here we assume that F is a rational map with no empty Fadot set. Here we do not require F is positively finite. The Fadot chain is defined by levels. A level 0 Fadot chain is the closure of a Fadot domain. A level 1 Fadot chain is the closure of the union of EK, where each EK is a continuum consists of finitely many level 0 Fado chains, and EK is contained in EK minus 1 and plus 1. Similarly, and inductively, we can define the level n plus 1 Fado chains from the level n Fado chains. This is a quite general definition. In fact, there are canonical Fado chains in each level. We call this canonical Fado chain the extremal chain. The lemma shows the existence of the extremal chain. For any level n Fado chain K0, there is a unique level n Fado chain K such that K0 is contained in K. And if another level n Fado chain K prime intersects K and the intersection point contains a Fado point, then this K prime must be contained in the K. So we call such K an extremal chain of level n. It's not difficult to show that the image of an extremal chain is also an extremal chain of the same level, and the pre-image of an extremal chain is the union of finitely many extremal chains. By this fact, we obtain a dynamical construction of extremal chains. Let Z0 be a component of the union of all periodic level n extremal chains. Then the closure of the union of EK is a level n plus 1 extremal chain, where EK is the component of F inverse PK E0 containing E0. Here P is the period of E0. So this is the dynamical construction of extremal chain. By definition, a level n extremal chain is contained in a level n plus 1 extremal chain. But the strict growth will stop after finite step. That is, there is a capital N such that any Fado chain lies in a level n extremal chain. So this we call the level n extremal chain the maximal chain. We have another definition. That is, a Fado chain K is a maximal Fado chain if any Fado chain intersecting K is contained in K. This is just the level capital N extremal chain. We can prove that each Fado chain is contained in a maximal Fado chain. The image of a maximum Fado chain are maximum Fado chains. Furthermore, each component of the pre-image of a maximum Fado chain is a maximum Fado chain. This is a very strong property. So by this property, we can deduce a decomposition of the dynamics. As a corollary, we know that maximum Fado chains are eventually periodic. We see some example of maximum Fado chains. An extremal case is the Sabinski map, where each maximum Fado chain is the closure of a Fado domain. An opposite extremal case is the polynomial, where the entire sphere is a level 1 Fado chain. Similarly, for the Newton maps, the entire sphere is a level 2 Fado chain. In general, the Julia side is called cluster if the entire sphere is a maximum Fado chain. In a recent paper, Schleicher also called such a map a crochet rational map. We construct invariant graphs in maximum Fado chain. We prove that let K be a fixed maximum Fado chain, then there exists a graph in K such that it is homotopy to the intersection of K and the Julia side, and Fg is contained in G. Since the maximum Fado chain is a level capital N extremal chain, and the extremal chain is defined, inductively defined by the levels, so we can construct an invariant graph in a level n+1 extreme chain based on those in level n chains. This is the basic idea of construct the invariant graphs in the maximum Fadder chain. So we only need to show how to show the level 0 and the level 1 case. For simplicity, we assume that U is a fixed Fadder domain, and its closure generates a level 1 extreme chain. In the level 0 case, the invariant graph of level 0 has been constructed by the theorem 2. There is a graph gamma homotopic to the boundary of U where P. This is the theorem 2. So it's enough to it remains to obtain the required invariant graph G from this gamma. A natural way is to add some pre-periodic arc on gamma. So this is the base of infinity is the U, the fixed Fadder domain U, and the green part is a part of K. The red points are the marked points. So since the blue one, the blue Jordan curve is the invariant graph gamma. Since gamma is invariant, we hope the added arcs are growing from gamma. The growing means each point of the arc is iterated to gamma, except to this terminal point. So the key point of the proof is to show that there are enough pre-periodic growing arcs in K. Here, enough means each marked point in K can be joined to gamma by a growing arc, and the marked points separated by K are also separated by the union of growing arcs. This property guarantees that the obtained graph is homotopic to the intersection of K and the Julia set. Pre-periodic means pre-periodic near the terminal point. This guarantees the obtained graph is invariant, since the other points are eventually iterated to the invariant graph gamma. The idea of the argument can be explained by a simple model. So we suppose that the yellow one is the fixed Fadder domain. We claim that there are several pre-periodic internal rays such that their union separate the marked points. The proof is not difficult. For example, to find the pre-periodic arc, we start from any two internal rays with the same landing point. We define gamma n to be the nth iteration of gamma. Because P has finite points, so there is K and M such that the gamma K is isotopic to gamma M. Then by lifting, we obtain a sequence of alpha 1, alpha 2, such that alpha J converge to alpha. And this alpha is pre-periodic and isotopic to the gamma. This is the idea of the proof. However, since the topology of extremal chain is much more complicated than the closure of a Fadder domain, we must overcome several topological obstacles to generalize this argument to the extremal Fadder chains. For example, internal rays generalize to growing arcs, but the existence of internal rays is well known, and but we need to take some efforts to prove the existence of growing arcs. Now we define MF, the union of all maximum Fadder chains intersecting P. We have proved that there exists invariant disconnected graphs in MF. To find a global invariant graph, we need to study the dynamics on the complementary of MF. We hope that the dynamics is either trivial or Sabin-Select. I will explain what does this mean later. However, it is not always true. We first see two examples. In this example, each small basilica is a maximal Fado chain. Their complementary is a Sierpinski-like map. In this example, each maximal Fado chain is two connected. In their complementary, there is a buried Julia set like this. So this is not a Sierpinski-like map. We first clarify what does Sierpinski-like mean. Let Fp be a marked rational map. A map F from V1 to V is an exact subsystem of Fp if the following condition holds. First, V has finite components and each component is a finite connected domain. And V contains no attracting cycles and the boundary of V is in the Julia set. V1 is contained in V and it is the union of some components of F inverse V. The final condition is essential. It says that each component of V minus V1 is a continuum disjoint from P. We first see a picture of the exact subsystem here. The middle is the exact subsystem. The pens is V, and the yellow one is V1. The left one we call the proper subsystem. In the literature, it is also called the rational-like map. And the right one we call the mixing subsystem. This is the exact subsystem. From the definition, we see that the boundary of V is contained in the boundary of V1. Moreover, each component of V contains a unit component of V1. From this point, we can define a self map. We can define a self map on the components of V. It maps F star maps V, and the image of F star V is the image of FV1. Then each component of V is pre-periodic and F star. Now, Sierpinski-like map means exact subsystem of Fp. The following theorem tells us why we call the exact subsystem Sierpinski-like map. Since each component of V is eventually periodic, so we assume that V is connected. That is, V is a domain. Then we define Vn to be the nth preimage of V contained in V1. Then Vn is a decreasing sequence of domains, and we define E to be the intersection of the closure of Vn. Then Fvn plus 1 to Vn is a proper map, and Fe equals to E. The following theorem characterizes the dynamics of F on E. There is a Sierpinski map G and a continuous self-map pi on the sphere, such that pi maps the Julia set of G onto E, and the dynamics of F on E can be blown up to the dynamics of the rational map G on its Julia set. Then we will see the fibers of the map pi. If they belongs to the intersection of Vn, then pi inverse Z is a single point. The other, if Z is not in the intersection of Vn, then Z must belong to a component of the sphere minus Vn for some n. So if B is a component of the sphere minus Vn, then pi inverse B is the closure of the Fado domain of G. This theorem characterizes the dynamics of F on E, and it says that it blows up to the Sierpinski dynamics. The key point of the proof is Thurston theorem and a combinatory criteria of submissive map. Now we begin to state the decomposition theorem of PCF map. We define the stable set. Let F be a rational map and K be a finite disjoint union of continuum. We call K a stable set if K is F invariant, and each component of F inverse K is either a component of K or disjoint from K. For example, recall that MF denotes the union of all marked maximum Fadot chain. Then the intersection of MF and the Julia set is a stable set. Moreover, each component of a stable set is eventually periodic. The dynamics on the stable set is clear in the PCF case. Let F be a PCF rational map and K be a connected stable set of F. Then there is a PCF rational map G and a quasi-conformal map phi of the sphere, such that phi maps K to the Julia set of G, and the dynamic of F on K is conjugated to the dynamics of G on the Julia set. So we call G the renormalization of F on K. We first establish the exact decomposition theorem. The theorem says that let FP be a marked rational map with non-empty Fadot set. Then there is a stable set K containing the marked Fadot set, containing the marked maximum Fadot chain, such that the stable set K induces an exact decomposition. This means that either V is empty or F V1 to V is an exact subsystem. Here, V and V1 are the union of all complex type components, complex type complementary components of K and F inverse K respectively. Complex type means a domain V is complex type if the following equality holds. Usually, the maximal Fadot chain, the marked maximal Fadot chain, do not induce an exact decomposition. The following are possible subsystems induced by the marked maximal Fadot chain MF. The proper one, exact one, and the mixing one. We show how to obtain the desired stable K from MF. For a proper subsystem, the non-escaping set is a stable set. We add this stable set to MF so that this subsystem is eliminated. The proper subsystem. For mixing subsystem, we will combine some mixing subsystem to form a new proper subsystem. This show like the picture. We combine some mixing system to form a new proper system and then reduce to the first case. So finally, the remaining subsystems are all exact. For an exact decomposition, the exact subsystem can be blown up to subinstancy map, but the renormalization on the stable side are also complicated. So we continue to decompose this renormalization. The detailed proof is as follows. We recall that the Julia set is a cluster if the sphere is a maximal Fadot chain. A periodic component K of a stable set is called a cluster if the renormalization of F on K has a cluster Julia set. We apply theorem 6. We obtain a stable set K1 containing the marked maximum Fadot chain, and that induces an exact decomposition. The periodic components of K1 correspond to the renormalization rational map GI. if each GI has a cluster Julia set, then the decomposition is over. Otherwise, we will apply theorem 6 again to this rational map GI. We obtain a stable set K2, such that K2 is contained in K1, and also contained in the marked Zimmer-Fadder chain. Continuing this progress inductively, we obtain a sequence of decreasing stable set Kn. This process must stop at finite steps. The final renormalizations are all cluster maps. Therefore, we have the cluster exact decomposition. This is the final decomposition theorem, cluster exact decomposition. Let FP be a marked rational map with non-empty Fadder set. Then there is a stable set K, whose components are clustered, such that K induces an exact subsystem. A result similar to our theorem 7 was proved in a recent paper of Schleicher's group. In this paper, they call the cluster map a Cauchy map. Now we can prove the main theory under this preparation. Firstly, by the cluster exact decomposition, the sphere are divided into 4 parts. Some clusters, exact subsystem, annular system, and some trivial system. So in the cluster, by theorem 4, there are F invariant graphs in clusters. For the exact subsystem, we can blow up the system to some Sabinski rational maps. But for Sabinski rational map, it is known that there exist Fn invariant Jordan curves. So combining these 2 points, we obtain the Fn invariant graphs in exact subsystem. For annular subsystem, we can find invariant arcs to join the invariant graphs in these 2 parts. Finally, the union of all these invariant graphs will be a global invariant graph. So we prove the main theory. Finally, I want to talk about the iteration number n in the theorem. So in our proof, the n appears only in the second steps. This n comes from the Fn invariant Jordan curve of Sabinski rational map. So the iteration number n can be taken to 1 if the following sentence is proved is true. That is, if we can prove that any marked rational map GQ with Sabinski Julia set or the Julia set or the empty Fadder set admits a G invariant graph containing Q. If we prove this point, then the iteration number n in our main theory can be taken to 1. Okay, my talk is closed. Is over. Thank you very much.
Thank you. Let's thank the speaker. And let me open the discussion. Any comments or questions? Can you maybe go back to your last slide?
Well, which one? Which page?
This one. No. I mean the slide.
Previous?
No, the very last slide, except thank you slide. I mean, where you said that if this sentence is true, then
the previous or later?
Later. No. I mean, toward the very last slide of your talk. I mean, slide 35.
Very last, right? Very
yeah,
last.
Very last.
Very last, yeah.
Yes, the iteration. Yeah, exactly. This blue sentence. Do you have any sense Do you have any idea whether an invariant graph for a post-critically finite or for a marked rational map can be found when the Julia set is the whole sphere? Do you have any ideas about this or any opinion? Do you think?
In fact, it's only need to prove this for this case, and the Julia set is the
sure.
sphere.
Do you have any speculation or any idea or
no. I have no idea how to find an F invariant graph.
Yeah, when with Daniel Meyer we worked on this. I mean, we thought very hard about this question, but
okay.
So are there other comments or questions?
Can I ask a question?
Okay.
So when you say a marked rational map, it's already a PCF?
PCF, right.
Post-critical set can be marked and you can increase the marked set. Okay.
Yeah.
But did you mention that in the middle of the talk that you can deal with non-PCF maps?
Yeah. The definition of maximum photo chain is not the PCF. Yeah, here.
Yeah, but in that case, can you find any invariant graph in general when the map is not PCF?
No, I don't know, because in the general case there is no expanding property for the map.
Oh, okay. So this is just for definition for non-PCF.
Yeah. The definition of maximum photo chain does not need the PCF, but if we want to find the graph, we need the PCF property.
So how unique is the graph you find? If you find the two graphs?
It's not unique. It's not canonical graph.
But for example, you have for polynomials, you use the half circles for the boundary of repeated equal component. Can you take the other side of half circle?
Yes.
You can still get
there are some choices of the half circle.
But can you say that they are like homotopic or isotopic?
Isotopic. Yeah, isotopic, right? Isotopic.
Well, I'm asking this question because I studied the matings of polynomials. And in that case, it's not exactly the problem of invariant graph, but there's a similar starting point. And in the case of matings, there are shared matings that comes from totally different topology for the same rational map. So I wonder if your theory can lead to something like that. So two totally different embedding on the graph for the same rational maps.
Yes, for do you want to know that for a rational map there are two kinds of different
so non-homotopic, non-isotopic graphs representing the same rational map.
Yes, because just for the special case, for example, here for this case, for the special case here, even for this special case, empty photo size, there is invariant Jordan curves passing to the post-grid points, but this curves, we can given any Jordan curve, we can find. In fact, given any Jordan curve, there is a Fn invariant Jordan curve isotopic to this curve. So in this case, it's not, even in this case, it's not unique. But I think for the cluster map, it's basically the unique. For cluster map, the invariant graph is basically unique. For example, under the homotopy or isotopy, this is right, I think. But for this case, or the Sabinski case, this is not unique.
So for general cases, it's far from unique.
Far from unique, because yes.
Okay, thank you very much.
Are there other comments or questions?
I have a comment, and so Dima Duco and Dylan Thurston and myself are also interested in this informal entropy graph PCF maps, and we realized that it's very difficult to answer whether there with infinite entropies realize the minimum for like Sierpin's carpet maps. So do you know whether this infinite entropy is realized as minimal invariant graph? And if so, then yeah, this infinite entropy is related to some dynamical property.
So what's the I don't quite.
So you define the core entropy as the infimum of the entropy of invariant graphs.
Yeah. I don't define. I just
Maybe
I don't
suggestion.
define. I don't. Yeah. I don't know how to define. I just try whether this is reasonable to define. Yeah.
Yeah, but I'm also investigating that. Yeah, infimum entropy.
What's this female entropy? What does mean female?
I mean infimum of entropies of invariant graphs. Yeah, the last sentence of this slide.
Okay. What does it mean? This is not reasonable.
So do you know whether this infimum is realized at the minimum of invariant graphs?
I don't know. Just some idea, some yeah.
And do you have any thoughts on what dynamical properties related to this infimum entropy?
I haven't. We haven't clearly think about this problem. Yeah.
Insung, I think this is a very good question. I mean, we've thought about similar things when we constructed these invariant curves, but to my understanding, essentially nothing much is known about these things.
Oh yeah.
Polynomial case. So I think this has not at all been studied in the rational case, and I think it would be very interesting actually to.
Yeah, in the polynomial case, we define the entropy, the core entropy defined on the Hilbert tree, and we can also define like the revising Hilbert tree to the Julia side. This similar, but in general case, yeah.
Are there other comments or questions?
I have a question. So how fractal this graph can be?
Fractal, that's a good question. Fractal. The construction depends on the expanding matrix. So in many parts, this is
for example, can you see, okay, this kind of graph can have a big dimension or something like that?
No, I think I didn't okay. I didn't think about this. Okay, that's a good question.
Well, in this Jordan curve case that you mentioned, these invariant Jordan curves for PCF maps whose Julia set is the whole sphere, you can say that they're actually quasi-circles. So I might speculate, you know, that the arcs here maybe are also quasi-arcs or something like this. I mean, the edges of the graph.
Yeah, but some intersection point. I don't know. Yeah, in most part is quasi-circle, quasi-arc. But in some points, connecting points, I didn't see. I don't know. Maybe in each edge is a quasi-arc. Each edge of the graph is a quasi-arc.
So you can think as a limit of some analytic curves, right? Each edge can be think as a limit of some analytic curve, right?
Yeah. Right. Basically, this yes.
Are there other comments or questions? Doesn't seem to be the case, so let's thank the speaker again.
Thank you.